Okay, in this example we have a slightly different situation going on, where instead of having squares as our cross-sections, now we have equilateral triangles as our cross-sections, and again a slightly different function as well. So to get started, I'm first going to just draw a quick little sketch of my curve. In this case, y equals x cubed over 4, which is going to look something like this. And I'm going to set up my solid from 0 to 3. So there's where my solid exists in that region. And we're told here that the cross-sections perpendicular to the x-axis are equilateral triangles. So if I put a little strip in here in my region, this is going to be the side of an equilateral triangle. And the height of that is going to be based off of the function. And so I'll draw an example of my cross-section here. I'm going to blow that up a little bit larger so we've got a little bit more room. But this distance right here is the one that's sitting in the plane in that region. And so it has a length of x to the third over 4. And now I need to come up with an area for this equilateral triangle. Now at this point, we have a few options. You should all be very familiar with the concept of 30, 60, 90 triangles, and we can use that concept to find the height of this particular equilateral triangle. And it shouldn't be too difficult for us because the side opposite the 90-degree angle is the same as the base of the equilateral triangle. And so this side up here is x to the third over 4, which makes the side opposite the 30-degree angle, which is this right here, makes it half of that, or x to the third over 8. And it makes this dimension, which is going to be the height of the triangle, that's going to be x to the third over 8 times the square root of 3. Okay, so now the area of this triangle is going to be 1/2 times the base times the height. So our cross-sectional area is going to be 1/2 times the base, which is x to the third over 4, times the height, which is x to the third root 3 all over 8. And this simplifies to an area of x to the 6th times the square root of 3 all over, looks like 64. Okay, and that's a formula for the area of our cross-section. Little side note here, there is a handy formula for the area of an equilateral triangle, any equilateral triangle, that I myself frequently use. Pretty much any time I have an equilateral triangle and I know the length of the side, no matter what, the area of the equilateral triangle is the square root of 3 over 4 times the length of the side squared. If I did the area that way in this problem, it would just be the area equals root 3 over 4 times x to the third over 4, the quantity squared, which gives you the same area that we found the other way, except a lot quicker and more efficiently. Okay, so now that I have that cross-sectional area, finding the actual volume of the solid is pretty darn simple. We can bring the constant out in front of our integral. So we've got square root of 3 over 64 out in front of our integral. Our limits of integration are going to be from 0 to 3, since those are the endpoints of the region. And that leaves as our integrand x to the 6th. And now we want to just, again, integrate this. We can, again, choose to integrate by hand or choose to use our numerical integral feature on our graphing calculator. I'm going to, again, decide I'm going to integrate this by hand. Why not? I'm feeling kind of festive today. So this is going to be x to the 7th over 7, which we're going to evaluate from 0 to 3. If we go ahead and do that, we've got root 3 over 64 times 3 to the 7th over 7 minus 0 to the 7th over 7. 0 to the 7th over 7 we can do pretty simply. 3 to the 7th is a little bit more challenging. Let's see, 3 to the 7th, that's 3, 9, 27, 81, 243, 729, 2,187. And so we end up with 2,187 root 3 over 7 times 64, which should be 448. And so we end up with that. Not really sure what that is as a decimal, but if you want to, you can take that decimal and compare it to what you would get with the numerical integral on this particular problem, and make sure that what we've done is correct. And there's your second example.